Okay, so now we're going to look at a timeline of these events. 1940s, 1950s, new particles are being discovered. What's called the particle zoo. Kaons and hyperons are being discovered. Lambda hyperons being discovered. 1964, Murray Gell-Mann and George Zweig. They propose quarks as mathematical tools, not actual fundamental particles, but simply mathematical tools in order to carry out calculations. This was due to the fact that scientists hadn't solved some problems. For example, quantum chromodynamics hadn't been discovered yet. And in addition, they hadn't solved the issue of fractional charges. And where this quantum chromodynamics comes in is from the Pauli exclusion principle, which states that no two identical fermions in the system can occupy the same quantum state. What this means for us is that if we have, say, two or three strange quarks, together to form a baryon, these strange quarks, three strange quarks at this point here, 1964, could not exist because of the fact that they had all the same quantum. They have two of them would have the same quantum number, which means that they would have had occupying the same quantum state. So, for example, this is going to be their their charge, and so we had to introduce a new quantum property, which was called color, in order to satisfy the Pauli exclusion principle. So now, because of color, say one of the strange quarks is going to be green, another blue, another red, which means that all three of them are occupying different quantum states, which means that the Pauli exclusion principle can still work. Now we're going to be looking, but now after the SLAC experiment, this was in 1968, we know that electrons, they interact with charged particles via the electromagnetic force. As from our de Broglie wavelength, we know that wavelength is equal to our Planck constant over momentum. So when we fire, so what the experiment did was firing a bunch of high energy protons, high energy electrons as a proton. And what this would do is that because we've increased their energy, their momentum, the electrons have shorter wavelengths, which allows them to interact with the up and down quarks within the proton. Okay, this is similar to the Rutherford gold foil experiment, except at a much smaller scale. And this proved that there were point-like constituents within the proton, and that these protons, these neutrons, were all comprised of quarks. Okay, so now that we've understood what strangeness is, strangeness being just the quantum number that describes the fact that a particle contains a strange or anti-strange quark, the reasoning behind why they're called strange quarks was simply because of the fact that when the strange particles, such as kaons and lambda hyperons, were discovered, the entire concept of quarks did not exist yet. So when we say when we called the kaon a strange particle, we were referring to the fact that we didn't know that there was that there were quarks inside it, and so scientists didn't know why it only decayed through the weak force, which meant that they called it a strange particle because it was only decaying through the weak interaction. They didn't know why it had a conserved quantum number that had to be conserved. it was only later when they found out that there were actually quarks inside the kaon that they called them strange quarks, and this is how this is how it led to basically us having strange quarks and anti-strange quarks. The reason why the strange quark has strangeness -1, anti-strange has strangeness +1, is simply due to the fact that scientists simply nowadays, what we like to call, they just said that the kaon would have had, say, positive strangeness, lambda hyperon had negative strangeness, which meant that strangeness was still conserved through the strong interaction, as we saw from previously. It just meant that when they discovered the actual quarks inside this, it just so happened that the kaon had a strange an anti-strange quark inside it, and the lambda hyperon had a strange quark inside it, which meant that the quantum number for each just stuck. The calculations, it didn't make a difference in the calculations, so that's why our strange quarks have strangeness -1, anti-strange +1. Moving on, now we're going to discuss a little about what strange matter could look like, but from the start we're going to look at our stars. So firstly, when we have, say, a star like our sun, it undergoes nuclear fusion. Okay, this is when it's fusing together very light elements into heavier elements and releasing a lot of energy. And the reason why it's doing this is it's fighting against the force of gravity, which is pushing all this matter into itself. And because the fusion and the gravity, they sort of balance each other out, means that our star, our sun, is stable, and it constantly releases quite a lot of energy. However, once our star has finished fusing together all this heavy material together, and the final stage of fusion is when it fuses iron together. So now, once it has an iron core, that iron core can no longer fuse together to create heavier elements and release energy, which means that what was once a fusion reaction which released a lot of energy, now we're not releasing as much energy to fight back against the gravity. So we have not as much fusion, but we still have the same amount of gravity, which means that gravity, in this case, gravity wins. So the star collapses into itself, okay? And it compresses itself into its iron core. Now, several things can happen, but what we're going to discuss is what happens when it compresses into a white dwarf star. Now, under the Chandrasekhar limit, which is around 1.4 solar masses, I believe, a white dwarf star can remain stable even against the force of gravity, and even though fusion isn't happening. Remember, we still have that iron core. So how is the white dwarf star still stable? Well, there's something inside the white dwarf star which is called electron degeneracy pressure. Now, electron degeneracy pressure is now fighting against the gravity, and what electron degeneracy pressure is that, remember back from our Pauli exclusion principle, no two identical fermions in a system can occupy the same quantum state. Now, this applies to electrons as well, which means that as we're compressing these electrons together, the electrons oppose this and oppose the force of gravity. and also due to Heisenberg's, and also related to this, Heisenberg's uncertainty principle also says that the more we know about a particle's position, the more uncertain its momentum is. So, if all these electrons are being squeezed in together, tighter and tighter together, right, that means that their position becomes more defined, which means that the momentum can take on a wider range of values, which means that within this star, we can get electrons with much higher momentums, which provides, which means that because the gravity is pushing in against the white dwarf star, electrons are pushing against it because they're occupying higher energy levels, and this is what keeps a white dwarf star stable. However, even this has a limit, as above the Chandrasekhar limit, special relativity begins to apply. Now, because these electrons are whizzing by so fast with such high momentums because of Heisenberg's uncertainty principle, this means that special relativity begins to apply because they begin to approach fractional speeds of light. And what this means is that where we had E equals mc squared, now we have to apply the Lorentz factor, which looks like v squared over c squared. What this means is that for relatively large increases in energy, we don't get back the same increase in kinetic energy. We instead get a much smaller increase in kinetic energy. Which is also the reason why mass doesn't go at the speed of light. Because as you approach the speed of light, we apply the Lorentz factor to its energy, which means that we have to essentially input infinite amount of energy to accelerate a mass to the speed of light. So what this means is that if the star is massive enough, this forces the electrons to be captured by the protons, and this means that and this is what our neutron star is. It's essentially comprised of a lot of neutrons where the electrons have been forced into the protons, and we get our neutron and a neutrino. And what keeps neutron stars together is the same principle. It's going to be our neutron degeneracy pressure, which same principle, Pauli exclusion principle, because neutrons are also fermions and they can't occupy the same quantum state, there's a pressure which keeps them apart. However, if we were to say go beyond this and force them into force a star to have even higher mass, this is where we can get our hypothetical strange stars. It is theorized that in these quark stars, it may be more energetically favorable for some of these quarks to become strange quarks. Because as you remember, Pauli exclusion principle says that no two identical fermions in the system can occupy the same quantum state. So some of these say, up quarks or down quarks, if they become strange quarks, they no longer are identical fermions. Instead, they are different, because as remember, a strange quark and an up quark, there are two different fermions, which means that we can lower the Fermi energy of the system. Now, we're not going to look into this today, but what this means is that, hypothetically speaking, we can get a core inside a star which is so extreme that we have these strange quarks being produced. And However, this is largely a theory. A lot of this research was done in 1984, and since then, not a lot of concrete evidence has been found for strange matter or strange stars. But still, an interesting concept to think about. So, that's the end of the video. I hope you found it informative, and I'll see you again next time. Thank you for watching.